Hello. In all the previous clips where we discussed control system design, we have focused on design of one degree of freedom control systems or control systems where we have only one controller available for us to tune. Now we have discussed a variety of off the shelf controllers that will do the job for us given disturbance rejection specifications, robustness requirements and so on. We have also looked at some special controllers such as the internal model controller, which we can exploit when we know something particular such as the frequency of the disturbance or the reference we want to track and so on and so forth. But at the end of the day, one degree of freedom control systems are not without their limitations. And what we shall do in this clip is to take a look at a couple of important limitations of one degree of freedom control systems, which would subsequently set the stage for us to discuss slightly more sophisticated control systems, namely 2 degree of freedom control systems, where we would have 2 controllers available to us for tuning. Now the most obvious and important drawback of a 1 degree of freedom control configuration is the fact that it is sensitive to measurement noise. This is something that we looked at fairly early on in this course, and to make that point again, I have drawn this block diagram of a control system where we have a single controller C and the plant P. The output of the plant is of course measured by a certain measurement system and is fed back and compared with the reference R. But invariably when we are making a measurement, we cannot avoid some measurement noise N creeping in and affecting the actual measurement. So what we are essentially therefore feeding back is not the exact measurement x, but we are feeding back x plus n. Now if we were to write down the transfer function that relates the output x to the reference R and the noise n, what we see is that the transfer function for both of them is exactly the same, namely Cp by 1 plus Cp, with the exception that there is a negative sign that multiplies this transfer function when we are looking at the relationship between the output and the noise. But magnitude wise they are both the same. And what is the disadvantage of this particular fact? It is that as control engineers we want our loop gain to be high within the frequency range where we want references to be tracked. In other words, our Cp has to be Cp of j omega has to be much greater than 1 within the frequency range where we want to track references and reject disturbances and so on and so forth. But in our effort to track references and reject disturbances, we also end up letting in noise within the same frequency range. And as you can see, there is nothing you can do about independently suppressing the effect of noise in comparison to the reference in this 1 degree of freedom control architecture. So over the entire frequency range where we are interested in tracking references, we are also going to be letting in measurement noise, and that is going to affect our output, and that is something that we do not desire and we do not wish for it to happen, but there is nothing we can do about it as far as 1 degree of freedom control structure is concerned. The second drawback has to do with the sensitivity of the transient response of this closed loop system to variation in plant parameters. So to remind you, the relationship between the overall transmission function T and the open loop transfer function C times P is given by T is equal to Cp by 1 plus Cp. And in the previous clips I have introduced the term Cp, the product of the controller transfer function and the plant transfer function, as what we call as L, or in other words a loop gain. And the term T, of course, we have introduced it as the transmission function. Now an important question that one might ask is whether this transmission function will remain the same when we have an uncertain plant on our hands. So when the plant P is uncertain or it has parameters whose exact numerical values we do not know and are therefore different from the nominal values that we might have assumed during design, or they have parameters that may be changing slowly with time, then it is obvious that our transmission function will also change when the plant model changes. The question that we want to answer is, how much relative change do you have in the transmission function, which I have denoted by the term delta t by t. How is this relative change or fractional change in the transmission function, how is that related to a small fractional change in the plant transfer function? Now this will allow us to identify one other problem associated with 1 degree of freedom control design, namely the sensitivity of the transient response of the closed loop system to changes in plant parameters. So let us first try to derive the relationship between delta t by t, which is the fractional change in the transmission function, and delta p by p, which is the fractional change in the plant transfer function for small changes in the plant transmission function. In other words, when delta p by p is much less than 1, what is the relationship between delta t by t and delta p by p? That is what we are out to do. So to do this, it is a little bit of algebra. So we note that t is going to be given by L by 1 plus L. So what this implies is that dt by dl is going to be equal to 1 by 1 plus L the whole square, or in other words dt is equal to dl by 1 plus L the square. Now we can replace dt with delta t for small changes in the transmission function t, and write the delta t is approximately equal to delta L by 1 plus L the whole square for corresponding small changes in the loop gain L. Now therefore delta t by t, which is the fractional change in the transmission function, is going to be equal to delta L by 1 plus L the whole square times t, and in place of t I shall write L by 1 plus L, because that is the definition for t, and what that gives us is that delta t by t is going to be equal to 1 by 1 plus L times delta L by L. Now let us focus on this term delta L by L. I shall write this separately on the left hand side. Delta L by L is going to be equal to delta of Cp divided by Cp, and this in turn is going to be equal to C times delta of P plus P times delta of C divided by Cp, or in other words it is going to be equal to delta P by P plus delta C by C. Now if we focus on these two terms, we note that since a controller is a system that we have designed as engineers, there is really no uncertainty associated with the controller structure. Hence we would have that in all cases delta C by C would be equal to 0, with the consequence therefore that the relationship between the uncertainty in the transmission function delta t by t and the uncertainty in the plant delta p by p is given by delta t by t is equal to 1 by 1 plus L times delta p by p. So delta p by p represents the fractional uncertainty in the plant's model, and delta t by t represents the corresponding fractional uncertainty in the transmission function, and the two are related by the term 1 by 1 plus L. So the term 1 by 1 plus L has a special name because of the relationship that it establishes between the variation in the plant's model or the uncertainty in the plant's model and the uncertainty in the transmission function. So it is therefore called as a sensitivity function. The reason it is called as a sensitivity function is evident from the equation that I have written here. It is the sensitivity of the overall transmission function to variation in plant parameters. Now we note that given the expression for a sensitivity function, which incidentally also happens to be the same transfer function that relates the output of our closed loop system to output disturbances, we note that the actual transmission function, which is t, which is given by L by 1 plus L, and the transmission function S, which is given by 1 by 1 plus L, have a special relationship, namely that T plus S is always going to be equal to 1 no matter what. So if we design the transmission function, then the sensitivity function automatically gets fixed and vice versa. Now how does the sensitivity function S look as function of frequency? We note that in the low frequency and the mid frequency range of our open loop system, our loop gain L is generally going to be very high, because we would have some performance specification to satisfy in these frequency ranges, either in the form of disturbance rejection or in terms of robust tracking or some such specification. Hence in these frequency ranges the loop gain L is going to be very large, with the consequence that the sensitivity function S, which is 1 by 1 plus L, is going to be a very small number in this frequency range. And if we take the logarithm of the sensitivity function, because if one were to try to draw the Bode plot of the sensitivity function, then we would note that in this frequency range, in the frequency range where we are expecting control performance, the logarithm of the sensitivity function is going to be a large negative number, because the sensitivity function itself is going to be a number that is going to be very close to 0. However, there will be a frequency at which the loop gain will start to reduce in magnitude, and at the gain crossover frequency the loop gain's magnitude will be exactly equal to 1. So in the neighborhood of the gain crossover frequency, the loop gain will change its magnitude from some value greater than 0 dB to some value less than 0 dB. And what about the phase in the vicinity of the gain crossover frequency? In the vicinity of the gain crossover frequency, the phase lag of the open loop system is going to be close to 180 degrees. Of course, it will not be exactly equal to 180 degrees, because there will be a certain phase margin for our open loop system, but it is going to be close to 180 degrees. So what will the magnitude of 1 plus L be, therefore, at frequencies that are close to the gain crossover frequency? To answer this question, let us draw the Nyquist plot for the loop gain. So the x axis is of course the real part of L, and the y axis is the imaginary part of L, and the critical point -1 is located here. So when we are near the gain crossover frequency, our loop gain will be located somewhere here, because the phase lag associated with the loop gain will be some negative angle which is going to still be greater than -180 degrees, and the magnitude will be close to 1. So it will be the radius vector for the loop gain L of j omega would have a magnitude close to that of unity. So if this is the unit circle, then the loop gain L of j omega will lie somewhere close to the circumference of this unit circle. So given the location of L of j omega in the Nyquist plot for frequencies omega close to the gain crossover frequency, what can we say about the magnitude of 1 plus L? We note that if this is L, then this complex number, which starts at the point -1, 0 and ends at the loop gain, is the complex number 1 plus L. And we note that if the angle of L of j omega is close to 180 degrees and its magnitude is close to 1, then the magnitude of 1 plus L will also be close to 0. And what does that imply? It implies then that the sensitivity function, the magnitude of the sensitivity function near the gain crossover frequency, which is going to be equal to 1 by the magnitude of 1 plus L, is going to be a number greater than 1 near the gain crossover frequency. And what does that imply given the definition of a sensitivity function? What that implies then is that our closed loop system is actually more sensitive to variation in plant parameters in this frequency range, in the frequency range where the magnitude of 1 plus L is less than unity, than the actual plant itself, because delta T by T is going to be equal to 1 by 1 plus L delta P by P, which in turn implies that the magnitude of delta T by T is going to be equal to the magnitude of 1 by 1 plus L times the magnitude of delta P by P. And if the magnitude of 1 by 1 plus L is greater than 1, then we would have that the magnitude of delta T by T would be greater than the magnitude of delta P by P. So in this frequency range, we are actually doing the opposite of what we as control engineers wish to do. In other words, we would end up with a closed loop system whose response is more sensitive to plant parameter variations in this frequency range than that of the open loop uncertain plant itself. Indeed, I have in the next slide plotted the sensitivity function for the overall closed loop system that we had when we undertook the design using Bode plots. So, to remind you, we had the plant P to be equal to 10 by S by 10 plus 1 times S by 50 plus 1 times S by 300 plus 1. This was the plant transfer function, and the controller transfer function, which was the PID controller that we ended up designing towards the end of the clip, was C was equal to 6 times S plus 1 by S times S by 170 plus 1 divided by S by 1700 plus 1. Now, for L is equal to C times P, I have plotted the sensitivity function S is equal to 1 by 1 plus L, and the magnitude of S as function of frequency and the phase of S with function of frequency is shown here. What is important is the magnitude of S, because that is what is going to determine our control performance, and as you can see, it is a very small number in the frequency range where we are interested in performance, or when it expressed in decibels, it is a large negative value, minus 60 dB, minus 80 dB and so on and so forth. As frequency increases, the sensitivity also increases, and there is a particular frequency, namely 140 Hertz, at which the sensitivity becomes greater than 0 dB. Now, what this implies when we go back to the expression delta T by T is equal to magnitude of delta T by T is equal to magnitude of 1 by 1 plus L times magnitude of delta P by P. What this implies therefore is that for frequencies beyond 140 Hertz, the fractional change of the overall transmission function is more than the fractional change of the plant itself. Therefore, the overall closed loop system is more sensitive to variations in the plant parameters than the case when we did not have feedback at all in place. Now, this might be okay provided the frequency 140 Hertz happens to be well outside the closed loop bandwidth of our closed loop system, or in other words, if 140 Hertz is a frequency that is significantly to the right of the overall bandwidth of T of S, then we would not have any problems, because even if our closed loop system is more sensitive to variation in parameters in that frequency range, we are anyway not interested in tracking performance or disturbance reduction in that frequency range, so that sensitivity will not affect our system in any particular manner. But unfortunately, that is not the case. If we were to plot the transmission function T that has been shown by the curve here, we see that its bandwidth is 315 Hertz. So, from 140 Hertz all the way to 315 Hertz, we have a sensitivity that is greater than 0 dB, or our closed loop system is more sensitive to variation in the plant parameters than an open loop system without feedback would be. And there is nothing we can do about this, because T plus S is equal to 1. So, we cannot independently engineer our transmission function to have a much smaller bandwidth than 140 Hertz, or equivalently we cannot engineer a sensitivity function to have a much higher frequency at which it reaches 0 dB than 315 Hertz, because of this identity, namely T plus S is equal to 1, and there is nothing we can do about it if we are stuck with 1 degree of freedom control architecture. Hence, the inability to independently design the sensitivity function S and a transmission function T happens to be an important drawback of 1 degree of freedom control architecture, and the consequence of that is that we are going to have significant sensitivity of the overall closed loop system in the frequency range beyond 140 Hertz to changes in the plant parameters, and that in turn manifests itself as large variation in the transient response of our closed loop system when our plant parameters change. So for example, in this case the blue curve here plots the overall closed loop system's transient response, step response for the kind of plant that we have picked and for the kind of controller that we have chosen here. This is the nominal plant and this is the controller. Now if the plant's gain were to increase by 20%, then there is this huge change in the step response. So the green curve here shows the step response of the closed loop system when the plant's gain has increased by 20%. Likewise, if the plant's gain were to drop by 20%, then the overall transient response of the closed loop system follows the red curve that is shown here. So you see therefore that when the plant's model changes a little bit, in this case its gain has either increased by 20% or decreased by 20%, the transient response of the closed loop system changes dramatically. It goes from the nominal response, which is shown by the blue curve, to the green curve when the gain increases, or to the red curve when the gain decreases, and there is a dramatic change in the response. The question now is, how can we minimize the variation in the transient response of our closed loop system when we have changes in the plant parameters, or in other words, how can we achieve robustness in the overall response of our closed loop system to variation in plant parameters. It turns out that it is not something that we can effectively accomplish by using 1 degree of freedom control architecture, and in its place therefore we would have to employ 2 degree of freedom control architecture, where we would have 2 transfer functions available for tuning. So both these examples that I just talked about, the sensitivity of the 1 degree of freedom control architecture to noise and our inability to suppress noise in the frequency range where we want to track a certain reference, number 1, and number 2, the inability to independently design the transmission function and a sensitivity function, which leads us to this excessive sensitivity of our closed loop system's transient response to variations in plant parameters, turns out to be 2 important drawbacks of the 1 degree of freedom control architecture. What we will see now is how we can address this issue by having one more controller available for us to tune. Thank you.